All right, our first speaker is David Legates. He is a climatologist who specializes in hydroclimatology, which is water, no surprise, statistical methods, climate change, and environmental education. He is the director of the Delaware Environmental Observing System at the University of Delaware. He is an associate professor in the Department of Geology and an adjunct professor in the Physical Ocean Science and Engineering program and the Department of Statistics. He serves as Delaware State climatologist. Please join with me in welcoming David.
Thank you very much. It's a pleasure and an honor to be here at, I guess, what's now Woodstock for the skeptic community. In any event, first of all, I have to also apologize. I was out of town last week and didn't realize I was in a paleo session, and I hadn't planned on saying anything about paleoclimatology. So I have thrown in a slide just in case, but nevertheless, I apologize. I was introduced as being a Delaware State climatologist, and as many of you may remember last year about this time, there was a big dust-up in Delaware, also in Oregon and in Virginia, where in those two states, the governor summarily fired the state climatologists, George Taylor and Pat Michaels, respectively. And the News Journal attempted to do the same with me, to have the governor fire me for my views on climate change. I do this disclaimer. It's sort of tongue-in-cheek because, as she said, most people should already know this, but the Delaware State climatologist represents neither the executive, legislature, nor the judicial branches of government. It does not speak for the governor or any other state agency or official. I speak for myself. Thank you. And the reason, too, is even though the governor and I see completely differently on climate change and what should be done about it, there's one thing we do agree upon, and that is that it was a recent media confusion of events associated that generated media coverage, I should say, that generated confusion as to the role of the state climatologist. Of course, the News Journal reported about a week later that Minter said my work with private groups and privately backed publications disputing climate change generated the confusion. The interesting thing is, on Saturday, front page was an article that I was coming here and that the Union of Concerned Scientists was apparently concerned. But nevertheless, they went to the governor, and her spokeswoman said that she does not object to my appearance at the Heartland Institute. And the interesting thing was they had two other gentlemen comment. One says, I think crucifying a man probably is more harm than good, because the Flames people are looking for the argument global warming is a conspiracy of nuts, leftists, and environmental extremists. They are both, I would say, either nuts, leftists, or environmental extremists. In fact, one of them believes that by 2100, temperature will rise about 80 degrees Celsius and sea level will rise 300 feet. His rationale is methane hydrates. He's entitled to his view, but it is certainly not mainstream. Now on to the discussion. I'm sorry? He's not entitled to his facts, but he's entitled to his view. So what I want to talk on today is global warming and the hydrologic cycle, because as I said, as a hydroclimatologist, I'm very interested in how that affects precipitation, in particular in the results of that, which is either floods or droughts, too much, not enough water. I take these from Al Gore to give you an idea as to where I'm going and where he's been. In particular, he says the number of large flood events has increased decade by decade on every continent, not will increase, but has increased. So it's past tense. And the amount of precipitation has increased globally in the last century by almost 20%. So one of the things we want to look at is, have floods increased? Has precipitation increased 20%? Also, global warming, ironically, while causing more floods, causes also more droughts. It also causes lower temperatures, I've recently learned. But nevertheless, it increases precipitation worldwide. It also sucks more moisture out of the soil, and I apologize for having to use such highly technical terms. But nevertheless, because essentially temperature rises, you have more water being sucked out of the soil, and so as a result, that leads to more droughts. So we want to look at what in particular is the scientific evidence for changes in flood and drought frequencies. Now, the human perception of floods plays a really important role in this, because the way we define floods is simply stream flow above a certain threshold. It's not directly related to, or I shouldn't say it's not completely related to the climate, although there is a direct comparison, because when we have excess water in the streams, it is obviously generated by an amount of precipitation. If we haven't had much rain in a while, streams tend to drop, and that's sort of a given fact of nature. So we do need increased precipitation to create floods or a heavy rainfall event. But also it can be due to the timing and form of precipitation. If you remember back to the floods of the Red River several years ago, the idea is we had there rainfall on snow, which caused a rapid melt of snow. So we got a lot of extra water, not simply because of the rain, but also of the snow. It's also related to the soil antecedent moisture conditions. The idea is if we have rain falling on dry soil, some soil types will accept that water more readily, and in fact with clay soils it may actually become more of a hard pan, creating more of an immediate runoff. So it does depend on whether we're in a dry condition or a wet condition when the precipitation falls. It's also based on changes in urbanization. The idea that we have more cities coming about with more asphalt, more macadam, more concrete, more impervious surfaces doesn't allow for the water to infiltrate. It runs off, and as a result, that creates a faster flood peak. And also channelization of streams or levees. I spent a year and a half in Baton Rouge, southern Louisiana, LSU, and the state climatologist there, our former state climatologist, Jay Grimes, sort of characterizes the southern Mississippi there as a freeway with no on-ramp. The idea is we have channelized the Mississippi down there to keep the water in the channel, that some of the streams which normally use the Mississippi as their drainage basin aren't allowed to do so. And so the Comeet River, which is supposed to flow in the Mississippi, actually is forced to flow backwards. And you don't need to know a lot about hydrology to know streams don't flow backwards very well. So in particular, too, by the levee system on the upper Mississippi and the floods of '93, we also increased the flood peak, and when finally stress was placed on the levees and the levees broke, we got a large flood event that took place, which we might not have had nearly that significant of a flood had it not been for the channelization. So what we have to really do is look at the effects of urbanization and channelization. And in particular, urbanization plays a very key role. People ask me in the state, is Delaware experiencing an increase in floods? And I have to say unequivocally, yes. We have had more floods in the last 10 years than we had in, say, the previous 40 years. Really, is it anthropogenically caused? Well, yes, most definitely. Does it have anything to do with climate change? Very little, if any. The reason is changes in land use. Here's Talleyville. You don't need to know where it is. It's in northern Delaware. You can see here we've got a road going through. You can see lots of trees. You can see this is 1954 fields and so forth. And less than 50 years later, it looks like this. Now, you can't tell me that by putting all these streets in, all these buildings and so forth, you're not going to increase the runoff. In fact, you do. And since this happens not just in Talleyville, but all over northern Delaware and all over southeastern Pennsylvania, we've seen increased precipitation. Again, floods are increasing. It's anthropogenic, has little, if anything, to do with global warming. It's changes in land use, changes in things on this land surface. So what we've got to do is get away from that. We've got to get to those streams that are non-urbanized and non-channelized, be able to get away from those last two effects to look simply at the climatic impact on changes in floods. And Harry Linz and Jim Slack did this in 1999, and they concluded trends are most prevalent for the United States in the annual minimum and median flow categories and least prevalent in the maximum category, which leads them to conclude that the United States, conterminous United States, is getting wetter but less extreme. Now that is in fact consistent with our theory of global warming, which says under a warmer world, what we would expect is it's easier to warm cold, dry air than it is warm, moist air. So we should have greater warming in polar regions, less in the tropics. That should lessen the polar equator temperature gradient, and therefore warmer polar regions would reduce the gradient, lessen the overall frequency or intensity of storms, and in fact, historically, warmer periods have seen a decline in the number and severity of storms. I would argue that a wetter world that's less extreme is a better world. A little more water is always good, and certainly if it's not coming down in one huge deluge, that's going to be a good thing. When we look at data here, this is showing temperature from 1890, or excuse me, showing the percentage of the United States experiencing wetness as defined by the Palmer Drought Severity Index, which is a measure of drought, and you can also use it as a measure of wetness. looking at the other end of the spectrum. You can see there's a slight rise. I'll argue that's probably not statistically significant. But what characterizes this is variability. And that's one of the interesting things we have to remember about climate. Climate change is a fact of life. Climate does change. There's no such thing as a stable climate, and there's certainly to talk about climate stabilization is like trying to stop the sun from shining. So the idea here is that what we're looking at is variability. We also see lots of year-to-year fluctuations. And that's one of the big problems I have with climate models is that every year tends to look like every other year. And in reality, that is clearly not the way the world works. Let's go back to our question. Al Gore said 20% increase over the last 100 years in terms of precipitation. Now, if you've listened to earlier arguments by Bob Bowling, Pat Michaels, Ross McKittrick, you know that trying to come up with a temperature record is extremely difficult. Well, let me tell you, when it comes to precipitation, you ain't seen nothing yet. The problem is you've got a tremendous amount of interannual variability. You've got a very low spatial coherence. It could be raining on this side of New York City and dry as a bone on the other side. So you've got to have lots of data to be able to resolve this kind of variability. And the problem is we change instrumentation all the time. And while it's not just a mercury in-glass thermometer to an electronic sensor that can measure eddies a little bit better, these are completely different instruments, which some have wind shields to try to cut down the effect of wind. And when it comes to snowfall, some of these can have 20, 30, 40% differences in the ability to measure snowfall. So the problem is a lot of these things back here I have no faith in, and I'm not sure I have much faith in the curve anyway, but this is the best we can come up with. And if you look at it, we see the rate for the globe was 0.1% per decade, which equals 1% per century, which is 20 times less than what Al Gore insisted. However, if you look, it's not statistically significant, so in a sense, it's infinitely less than Al Gore suggested. Northern Hemisphere land, not statistically significant, and Southern Hemisphere land is a slight rise of 0.2% per decade, and that's not statistically significant. When we look at the same analysis by latitudinal bands, you can see that 3 stick out: 60 to 80 degrees north, 40 to 60 degrees north, and 20 to 40 degrees south. Any idea what the common theme among those 3 is? Very good, snow. Because remember, I said snow was a very problem measurement. And way back when, we didn't have much observations with snow shields that go on to try to get good observations. We've changed the instrumentation over time. Much of that has resulted not in a change in the actual snowfall, but a change in our ability to measure snow, sometimes on the order of several percentages. As a result, I believe that much of this rise, probably enough to make it significant, is due to changes in instrumentation, not really a true change. Southern Hemisphere, some of that's dominated by the Andes, may not be completely a snow signal, but nevertheless, certainly that would play some role there as well. Now, if you probably remember back in December, there was a neat study. 2 of them came out. The News Journal ran a report, Heavy Rainfall, is called Sign of Climate Change. And then they ran it the next day, apparently again, slow news days. Severe weather predicted as norm. I don't think this was a front page, so I've one up on this group. But the report was released by Environment America. It is intended to influence the debate in Washington over the Lieberman-Warner Climate Security Act of 2007. Surprisingly, why this came out right at this time. 3 things they said. Floods are increasing in Newcastle, in northern Delaware. Well, of course. Droughts are increasing. I'll explain why that's happening too. None of that has anything to do with climate. Okay? The third thing they did point out, though, is this statement, and this is statistically testable. Delaware has seen a 37% increase in storms, dumping 2 inches or more of rainfall over a 24-hour period. As a climatologist residing in the state of Delaware, I looked at that and said, there's no way I can buy that. I'm sorry. So I went to the data from the State Climate Office, which I have access to. And sure enough, there it is. I got data from Porter Reservoir in Wilmington, Delaware, days with precipitation greater than 20 inches. It goes back from 1940. And if you look at this rise, that's somewhere in the vicinity of 37%. I'm stunned, but I've got to give the facts. This is what they said, so there's nothing wrong with that statement. Except, of course, I went one step further. I looked at the data. Now, this has got a statistical issue I won't go into because I can't have 2.5 days. I can only have 2, 3, 4. So the numbers have to lie along those black lines. So we have integers over here, not floating point numbers. But if you notice, the R squared, the percentage of variance explained by the curve, just a tad over 5%. And if you remove the curve and try to decide whether you're going to make policy on that change, I don't think you'd want to. The other interesting thing is we also have 2 other stations in Newcastle County. One is at the airport, which is a National Weather Service first order weather station. You can see there has also been a slight rise here, but the correlation coefficient is so low that the percentage of variance explained is barely over 1%. And we have another cooperative station, which are daily observations taken by observers that give of their free time, much like the state climatologist of the state of Delaware. And also the state of Alabama, if John Christie's here, both of us operate free, without charge. But nevertheless, you can see a slight rise, but the percentage of variance explained just a little over 1%. Now, you wonder, why is the number so high at Porter Reservoir, even though it probably isn't statistically significant? I normally wouldn't have had a clue, but it turns out that there was a happen chance meeting about, I guess it was 2 months ago at Porter Reservoir. We're putting up a network of weather stations around the state. They're automatic weather stations. We have one at Porter Reservoir. They report every 5 minutes, and they're completely different than this measurement. One of the gentlemen came out and said, "Oh, that's cool, that's neat. I've seen this weather station. Can we get the data for it?" "Sure." "Is it available online in real time?" "Yes, it is." "Can I get the URL for it?" "Yes, for the 5th time, we can give you that URL." And he went on to explain then, well, that's good because when I miss those heavy rain events, literally, this is what he said, when I miss the heavy rain events because we're busy with a water treatment plant, I just go to the National Weather Service station over at the airport and write their data in. And now I can write your data in. So what I know is going on at this station, well, you go back to, that's what I get for, see page it. There we go. What I know is happening at this station is right out in this end, this guy is running in a situation where it's heavy rain. They're doing a water treatment plant for the city of Wilmington. And so instead of using the data from the station that you see, he's pulling data from another site over 7 kilometers away. So it's an inconsistent record. So I have no idea whether this is real or not anymore. And of course, it's not statistically significant. But we've gone to press 37% increase on a station that may have simply an inhomogeneity due to an observer bias. Oh well. What about droughts? The other end of the spectrum. Well, the idea of a drought, there's different ways of defining droughts. A hydrologic drought is simply stream flow or reservoir levels that fall below a certain given threshold. And in this case, it can be due to an amount of precipitation, in this case, a lack of precipitation for a long time period. The precipitation decreases or the runoff decreases. It can also be due to urbanization or an increase in water-intensive activities. People ask me, are droughts becoming more frequent in Newcastle County? And I can say unequivocally, northern Delaware, Newcastle County, yes, in fact, they are becoming more frequent. Is it anthropogenic? You bet. The population is exploding in northern Newcastle County, in northern Delaware. Okay, we've got all these new people on the demand side of the water system. What about the supply side? Well, precipitation climatology really isn't changing. So yes, it's happening. Yes, it's anthropogenic. No, it has nothing to do with carbon dioxide, has nothing to do with climate change, has everything again to do with land use changes. So the answer is yes, but for a completely different reason than an inconvenient truth would want you to believe, at least on this side of the Atlantic. Here's the percent area of the United States in severe and extreme drought as provided by the National Drought Mitigation Center. What you can see characterizing this, again, is high variability. Here is the peak associated with the Dust Bowl period. You see we go through a number of other dry periods, but we also go through periods where drought is very infrequent. The key indication is there is really no trend to this whatsoever. The fact that droughts have been increasing year after year is not there at all. In fact, they happen, they go away, they come back, they don't go away. Here's my slide that I throw in to make me part of a paleoclimate section. 2,000 years of drought in the central United States, Woodhouse and Overpeck concluded that the droughts of the 20th century are characterized by moderate severity and comparatively short duration relative to the full range of past drought variability. What we're seeing is not out of the ordinary. It's very much within what we would see, and in fact, we've seen worse in the past. Here shows them both together from NOAA. This is updated every couple months. Here you can see the percentage of area of the United States in dry conditions in red, wet conditions in green. Again, you see lots of variation, but really no significant trend. Now, the other people always ask me about climate models, and I don't like to talk about them much because they are a big-time can of worms when it comes to precipitation. I've always argued that the problem with precipitation, or the problem with climate model, is that anything you do wrong in the model will show up in precipitation. You get the topography in the wrong place or not as dramatic as it should be, which many models do. If you get the atmospheric circulation wrong, if you get the temperature structure of the atmosphere wrong, if you get anything wrong in a climate model, the land surface, moisture conditions, anything you get wrong will show up in precipitation. The problem is anything you do in precipitation that's wrong feeds back to the rest of the model. Why? Because energy goes into evaporating water and energy is released when water condenses. So you're goofing up significantly your energy balance, which is driving the temperature, driving the other structures such as atmospheric circulation, if you don't get the precipitation right. And many models, for example, see the United States as having a precipitation regime where, say, Fort Collins, Colorado is much wetter than Shreveport, Louisiana. Now, you don't have to be from a geography department to realize that's not really the way the real world works. But if the model doesn't see the world that way, how on earth are we going to believe, first of all, any changes it shows? But second of all, when you look at these models in detail, what you find out they actually simulate is what we call popcorn precipitation. They get the convection real well, but they don't get other larger scale circulations. So in a sense, what happens is it rains a little bit all the time, everywhere. It's almost like a Gladys Knight and the Pips song, seems like it's raining all over the world. But in any event, it rains, sorry, I know it's a bit old for the rest of you, but nevertheless, sorry. I digress. But nevertheless, in these models, it shows precipitation driven largely by convective processes. And I've always said, show me a climate simulation for, let's say, 12Z on March 3rd, 2085. And I know Tom Wigley, when I say that, says, no, you can't do that. We can't forecast that far in advance, and you can't expect me to forecast that far in advance. And the answer is that's exactly right. But what I want to see is that looks like a reasonable weather map. I want to see fronts. I want to see storms building. I don't care that I can't forecast that on that day it's going to rain in the morning and be clear by afternoon. But I want to know that the model is simulating the exact processes that drive climate. What I see, particularly with the case of precipitation, is I don't see the process. I see convection, and that's it. I don't see fronts. I don't see weather maps. I don't see process. So if the model doesn't have a process, it's a nice academic toy, but it doesn't tell me particularly what I need to know in terms of what's likely to happen, because the process that exists in the world today isn't simulated in the model. And again, I'm biased, but I think precipitation is a very, very important component of a climate model and of the climate system, because not only is it a mass balance, but also it's part of the energy balance. I'll leave you with this last slide. Here is showing the Canadian, well, I was going to leave you the last slide. Here we go. The Canadian climate, this is from the National Assessment 2001. If you remember back then, they chose two models. One was the Canadian model, which was the most extreme model in terms of temperature. The other was the Hadley model, which is the most extreme model in terms of precipitation. And in this case, it's cut out for just the Northeast, but this extends back to essentially 3/4 of the United States. Essentially, the Canadian model says precipitation isn't going to change much. What really is going to change is we're going to have a lot warmer temperatures, which is going to suck a lot more moisture out of the soil. Sorry again for using those technical terms. And as a result, we're going to see much drier conditions. On the other hand, the Hadley model was chosen largely because it had much more precipitation. And so what the Hadley model said was, even though the temperature is going to rise much more modestly, that's going to be offset by increased precipitation. So in fact, we're going to have a slightly positive world, which gives us, in this case, a little bit wetter world. So if you like droughts, It's the model on the left for you. If you like a little bit wetter conditions, it's the model on the right, and it really underscores the idea of the two climate model system, which says largely the person with one climate model always knows what the future is going to look like. The person with two climate models is never quite sure. Thank you very much.
Get that set up. Thank you very much for that presentation, David. As a native Utahn,